Hello everyone, I'm Paul Rossi.
I am Sine Fragoso.
And I'm Crystal Shi.
And we're the AIDE Onshape team. So to begin talking about what AIDE Onshape is, we're responsible for making the 3D models of Agua Clara's unit processes in the browser-based CAD software called Onshape, and then integrating them into Agua Clara's infrastructure design engine, or AIDE, which will allow anyone with a web browser to generate an accurate Agua Clara plant model on their own. And to accommodate for different plant layouts, the models we make need to be highly customizable for different plant layouts. So one of the most important things in Onshape that lets us do this is configuration variables, right? We can store variables in map variables like doser on the left, which contains useful information like bolt D in the middle, which is equated to things in our 3D models like this circle on the right, which is just equated to bolt D. However, sometimes we don't always get the supplied variables that are exactly what we need. Or sometimes we need more complex calculations than simply diameter equals bolt D. And here, FeatureScript, which is Onshape's proprietary coding language, comes in handy, right? Because it lets us write complex expressions that output geometric variables, which is helpful when, say, we need to use a continuous dimension to pick the right size of a part with discrete limited sizes, which is the case for most standardized parts. The example shown does just that. It uses code up on the top that takes in a continuous length input to calculate the best possible spacer to fit that length, and then outputs the ID of that spacer.
So something that we've been working on recently is a continuation of what we presented on at the symposium, and it's the lever arm mass balance. So calculating the dimensions of the float and counterweight needed to balance the lever arm. Next slide. So after receiving feedback from Monroe, we ended up including two new variables called the dosing error and safety factor. So the dosing error is a dimensionless quantity which determines the change in submergence as the sliders move. And so this ensures that there is not too big of an error in dosing. And so the change in submergence of the float is going to be equal to the max head loss times the dosing error. And then the safety factor is also dimensionless, and this is used to calculate the float thickness, since we want the float to be thick enough so that like any changes in submergence that happen when the lever arm moves won't really be significant. And so the float thickness is going to be equal to the change in submergence times the safety factor. Next slide. So here you can see the mass balance equations we used and the free body diagram, which is the same as last time. But you can see that we've updated our equations to include the new variables for the dosing error and the safety factor.
As part of our next task, we kind of had to work on the modeling and the integrating of the fasteners into the doser's lever arm. By modeling these fasteners, we created an actual fastener library where we had to kind of model the different types needed for the doser, and we actually included different configurations in order to kind of accommodate like the possible needed measurements within the lever arm. And we also had include the ability to choose between threaded and unthreaded fasteners. As part of the additions, we took into consideration the proper configurations to ensure all the parts were proportional, and we kind of also had to consider the parts that needed to be threaded. In these images, you can kind of visualize the types that we needed in different parts of the actual model.
Another feature we've been working on is creating a feature that can automatically choose a spacer or standoff configuration based on a max or min height input. And so this feature is necessary because our configurations have discrete lengths based on the part dimensions that we found online at Apex Fasteners. So a feature script feature is necessary in order to choose the configuration that best suits what we need it to be. So as you can see in the image, the spacer ID right there is a variable that is being set by the fulcrum spacer configurations a little bit earlier on in the feature tree. And so next slide. So for the fulcrum spacers, we want to ensure that the spacer is at least as tall as the bolt head used. And so this is to prevent collisions when the lever arm rotates. And so as you can see in these images, on the left side, we have a smaller bolt M3, and you can see that the spacer is at least as tall as that bolt. And then on the right side, you can see where we changed the bolt to an M8. And then in this one, the spacer is much bigger. And then the fulcrum is also smaller because we can change the fulcrum size based on the spacer size. So, and then for the float and fulcrum standoffs, we want to ensure that the standoffs chosen are the largest possible value that is less than the user inputted max. And so you can see on the images, that's like the little golden rod there. And so it determines like the spacing that connects the center part of the frame. Next slide.
And so now to show off a few of the tasks that we've been working on, let me give a live demonstration. So this is the doser, and as you can see, there are a lot of fasteners now incorporated into the design. So bolts, washers, spacers, threaded standoffs, that kind of thing. Right, that's clear to see. But something that's a little less obvious is that the size of the float and the counterweight are now dependent on some of the variables that we described previously. Right, so one thing that drives the thickness of this float and the size of the counterweight is now the safety factor, which determines the, I guess, assurance that this float will not become completely submerged or unsubmerged. So right now, the safety factor is set to 5. If I set it to 2, which means that we're okay with this float becoming unsubmerged a little more often, or with more risk of it becoming unsubmerged, the float becomes flatter. And the counterweight becomes smaller because it now has to balance out less weight. But this assumes that we can get a custom float and counterweight of a particular diameter, which is okay because we can. However, it isn't always convenient or feasible to get custom parts like that with certain standardized parts, especially like this threaded standoff in the middle here. Which sort of determines the space in between these two halves of the float, just by virtue of its length, right? But we want the user to be able to control this somehow. So to do that, we supply this frame swivel W underscore max variable, which determines the maximum spacing between these two halves of the frame. And right now you can see that this variable is set to 40 millimeters, which is great because we have a 40 millimeter spacer, right? That's why the distance between these two halves, as you can see in the bottom right, is 40 millimeters. However, if I were to change this to say 52 millimeters, well, we don't have a 52 millimeters threaded standoff. So our feature script gives us the next best thing, which is a 51 millimeter standoff. So our code effectively lets the user control this dimension without conflicting with the discrete number of lengths of our standardized parts.
As part of our future tasks, we have to make a few improvements and fixes to the doser. So we would have to kind of add feature scripts. So for other discrete link components on the lever arm, such as a threaded standoff, as you can see on the picture on the left, and also add some code that we would write to incorporate the new version of the doser into the entrance tank model, and the entrance tank model is also modeled on the right. Other than that, in the fall, we will kind of be working on whatever tasks arise from ongoing Onshape during the summer. And if you guys have any questions and recommendations, that would be deeply appreciated, and thank you for listening.
And as a final note, if you'd like to see any of the documents that we showed in this video, as well as summaries of what we talked about, that's all available in our slides and appendix slides on our Google Drive. Thank you.